Okay, now we are live. Let me close the window so it's not too noisy in my room. And here we are. I just received. So, this is about the USB hub. This is the next part. Let me make the camera a bit more straight. No, it's okay. Not sure how to. Okay, now it's straight. Let's remove this. The video works. So, let's remove the battery so it doesn't use the battery. So that's the next part in my custom USB hub design. I'll just make a quick recap. So I want a USB hub which is high quality, which has lots of protection, and which is meant for production testing. So each of the USB hub will have ESD protection, and you can remotely switch on and off the power of each of the ports. So you can restart devices remotely if you want to. This is very important if you do some testing, so CI testing of devices and so on. But not only can you switch on and off the power of the hubs, there will also be a power port where you can actually power some higher voltage device, anything between 6 volts and 40 volts. I think 6 and 40, something like that. Yeah, 6 to 40 volts. So here you can either provide the normal USB or 5 volts or 6 to 40 volts. And the 6 to 40 volts will also reach all the other ports, and when you switch off the USB port, it will also switch off the power. And this is when you have devices which use more than 5 volts or more than the 500 milliamps which are provided by more than the 500 milliamps which are allowed on the USB 2. So in the USB 2 spec you shouldn't be able to draw more than 500 milliamp, and I actually also have protection against that. So if you draw more, then it will switch off the power, and this is mainly because when you have a USB compliant 2 device, you shouldn't draw more, meaning there shouldn't be any issue. And if you draw more, it means that you have an issue in your design. And this prevents from the issue to the design getting fried itself and affecting all the other ones which are connected to the next port. So the first time I did the USB, it was in this form factor. Yep. And the idea behind that was to put it in one of my project boxes. They are big enough generally for all my projects, and there are standard boxes which you can buy everywhere. These boxes. So these fit this box. The problem with having two sides is that it is very compact, and you have to populate both sides. So on this side there was all the connectors, and on these sides there were all the components, most of the components. And if I want to mass produce, so currently at the beginning the design was just for myself, but if I want to mass produce it, then this is not doable. Having dual side load costs a lot of money. So I decided against my initial goal to have it in this box, and I will just print, because 3D printers are cheap and I have one. I will just print my own box, and since I want only not a lot of them, it's fine to print my own box. It probably also takes not much more time than putting holes correctly into this one, or having to design holes the right way into this one so it fits correctly. Well, just design and a box around this board. So this is the board. It's a lot larger. It's twice, yeah, almost twice as large, yeah. A bit less, but almost twice as large. But at least all the parts are now on one side. On the other side, there are still some parts you have to solder, but these are manual. These are things which you have to solder manually, through-hole components. So whatever happens, that doesn't matter, because this will be soldered by hand, and you don't have to re-put in a reflow oven. So even if it's when it's soldered by hand, it doesn't matter which side it is, because the operator can just flip the board. And I think not all, yeah. Most of the through-hole components are on this side, all the SMD components are on this side, with some exceptions, the switches. I can still change it and put some SMD switches. For now, I just reuse the switches which I had here. Do I have one here? Yeah. I just reuse these switches because I had the footprint and it was okay, and they are quite big and fine. But if I want to really mass produce, I think the switches, so I would have all the components on one side, all the SMD components on the other side, and this would use not a through-hole part but an SMD part. And I'm sure there are SMD switches which are plenty fine and robust, but that's not too important for now. But this is the second prototype, and also I had to redesign all tracks. So you see, I had to redesign everything, which took a bit of time, and then getting the parts took a bit of time. And now, today, we will solder it and see if it works. We will solder, again, we will solder part after part. For now, we will start with the power and see if the power works. And then we'll move on with the rest. And I also got the components. There are some components I didn't have. And the USB hub, I will put this in this box. I won't use it anymore. So I have most of my components. Let's switch some lights. A lot better, at least for me. I will also print the schematic so I know which parts and I'll show you the schematic, which parts I will have to place. Schematic. First I need to start cups. My printer server. Cups is started. PDF. That's the board. Where's the schematic? sch.pdf. There's the schematic. And yeah, the schematic, I changed it. It's now, let me show you. Can I? Yep. So it now fits an A4 previously. So the main part is here is on an A4, and then we have pages for all the other downstream ports. So this is the upstream port and the MCU, the USB hub. And we have all the downstream port which are on other pages, and this makes it a lot more readable. Actually, this is not, well, I want to print only this one for now. So let's print two laser jets. Yeah, one side, one copy, one page. Yep. So let's print that. And I did a lot of changes and a lot of fixes compared to the previous one, but we'll see them as I go. What I did also, we'll see afterwards. So, yep, I have my sheet, which I can now print, and the complete schematic is all the PDF. It's this one. F5 up. This is the complete schematic, and you see these are all the downstream ports, and we have 7 downstream ports. They are generated copy-paste, so I have a script which populates them. So I only design downstream port 1, and then I have a script which copies downstream port 1 and then enumerates correctly all the other ones. Up, and we will make this left part, and I should have received all the parts. So I received the boards yesterday, and I received the parts, the remaining parts, a couple of days, I think 1 or 2 days earlier. I didn't check if they're here, but I didn't have any issues with LCSC for not shipping the parts. So let's start. Let's get. Do I use? So we'll do only SMD components. No. This is the board, this is the hub, the input is here. So we'll again have the 5 volt, and I forgot, yep. This is a thing I didn't do. I have to put on the seal screen which one is 5 volt and which one is high voltage. So 6 volt to 20 volts. Here I did some seal screen to add some meaning here also, but I forgot on the switches, on the inputs. So this is the first thing I can note is Add power in silk description. Up. And I like paper because I can write my things on the paper, the changes I want to make on the paper. So this is the input. We will put it this way. The first board will only be to test the power. And afterwards we will test all things. I changed the footprint also. This was previously a generated foot. So they are always generated, but I said it was SMD component, a chip component like you have for capacitors and resistors, and this generated a large pad. Now this is a smaller pad, which is the manufacturer, the recommended design. And the change which I also made, I don't know if it's good or not, is you see there's no copper filling at all on the top and on the and on the bottom. It's empty. There is only ground in, so this is a 4-layer board in this layer just below this layer board, because when you do high-speed traces, what I recommend is that you have at least 5 times the width of the trace clear or next to the next clear or clearance. So I don't know if this clearance is only related to other signals, or if this clearance also includes copper planes, and to not have to bother and to have more than the 5 times minimum, I just removed all the copper. And I hope this is better for the impedance, but actually, yeah, this is something I've learned and I didn't find a lot of information about it. That I think I couldn't prove, but yeah. And yeah, on the back. So this here you see a copper filling. This is actually the shield. The shield, you want to have very low impedance. You want to have all the shields connected. So the shield on the upstream is connected to the shield on all the downstreams. We have resistors and capacitors somewhere in the input here. R1 and C1, 2 resistors and capacitors. So you can choose how to decouple or how to connect the ground to the shield. So that's it. Let's fire on the soldering iron. Let's clean this. We will start with, what do we start with? The USB inputs, or let's start with how the schematic is made from top to bottom. Makes it easier to cross the things. And for left to right. So first we will put some of these DC jacks. What is this? DC inputs. Yeah. We need 2 of them. Oh, Michael Minecraft. Okay, thanks. Since I have a viewer, which is quite rare, feel free to ask questions about this or any other work I'm doing. Since you're the only one, I can spend some time answering them. And for now, I will just solder that. The design, no, design is not online yet. It's open source, and I think I didn't push. Oh no, I didn't push it yet, this version. If you want to have a look, because I didn't solder it, and generally I push it only after I've added some more information and tested the first prototype. And currently there is no first prototype. Well, this is the one we are making, and once I have my comment if it works or not, then I can push the design and then you can see it. But I mean, you have the schematic on the right, so if you want to copy the design, just capture screen the schematic if you're too eager to wait for me to release the real source files. I have the wrong tip. So I did this is another product I was working on, but yeah, this is something which is really weird. Yeah, it's another product. Let's give it for another time. So I used a finer. You see this tip? It's a lot. It's a chisel tip. I think 1.2 millimeters, something like that. This is for real small SMD pins and connectors and so on, which works fine. But for huge work, I prefer to use this horse hoof style. Kind of soldering tip. They are really hard to get used to, but once you get used to, they do quite well the job. So we zoomed in a bit more, so you can see. Let me show you see the screen you are also seeing. Okay, and it's not heating, is it? Did I? Okay, it just takes a bit of time. This is VCC. So it shouldn't take too long to solder. Oh no, there is a huge copper plane behind it. So it does take a bit of time. And I purposely designed the connectors so they stick out a tiny bit. See on the edge they are not perfectly matched. This is because there will be a case and I don't want it to be too much inside the case, so the connectors do protrude a tiny bit. Power jacks. I'm wondering, they're quite fine, so I quite like them. They're really robust, but it's weird that there's kind of no other design or no standard way to have power inputs and so on. Well, this power input, so you see there's one for 5 volt, there's one for 12 volt input, but you can use any connector you want. There is no kind of standard way to say, if you use these measurements, it means that the voltage going to this port is 12 volts or is 5 volt. Everyone does whatever he wants. And there is also no kind of female-male thing. What if you want to have power from a board? So here, general up. No, I lost concentration. This is the power input. This is so I can provide power to the board. What if the board actually powers other devices? What connector do you use? I know no standard connector which says this is a power output and this is just the power input. So what I do is, for the power output, I use the exact same power thing than the power input, simply because the connector is very common. And while it's rare to use it for power output, it would work. But it's really weird that there's no power output standard and that there's no kind of standard what DC jack or standard. I wouldn't say a standard, but some common way to define what voltage goes to which pin, to which barrel jack connector. But just write on the seal screen what it is, and then it's fine. And here I don't know. I will write it with a pen. So J2 is 5 volts. This is 5 volts. This is the J3. This is 6 to 40 volts. I think 5 volts also could go in. It's badly written. Nah, at least I can read it. I know this is also the right one because of this screen. What I also changed, this is a capacitor which will be flying flat. This is one problem which we had with the other design. This capacitor is too high and wouldn't fit in the box, and it's really huge. And now I changed the design so it can lay flat on the board. Okay, so this is the power input. Let's also put the USB one. Do I have a USB connector here? Yep. I don't have all the parts in this box. I have just most of them. And I don't have a lot of them remaining. I can still order some. I only have 3. This is small batch prototype and this should be enough If I want more, I can order more. It's not like I'm in a rush. This design has been... Yeah, I started this design around Christmas, so it's already 6 months ago. So it's not a couple of more months that will make the difference. And this was because of a job I had where we do have voltage. We do have 12 volts. The target board uses 12 volts, and there was no way to really start it. For now, there's an operator switching on and off. I've created a relay, so it's really a mechanical relay with a custom board and some custom code where over serial you can start on and off, but there's no real way to do it. And this way you can actually do it. And you could just use a port to power on and off the high voltage power and not use the USB. Perfectly fine. So we have J3 that's done, J2 that's done, J1 that's done. We can now add the fast beats and let's start with USB and see if it works with USB. So fuses, the fuses are in my power book. Power. SMD book. Power devices are inside there, and I think the input is also power input 500 milliamp. It's blocked at 500 milliamps simply because this is the maximum allowed. So if this USB hub draws more than 500 milliamps, means we have an issue. Let's get some tweezers. Let's clean the tweezers so they don't stick. This is just alcohol with some water, 60%. The same thing you use to disinfect surfaces. It's 70% alcohol and 30% water. And simply because the alcohol is good for lots of cleaning stuff, but the alcohol is not the only solvent, and some things don't dissolve in alcohol, like salts. They need water. They dissolve quite well in water, but not in alcohol. So this is F1, and this is why I have 30% this liquid everywhere. It's easy to make. Let's put solder on one pad. Let's reheat the pad while I put this fuse. I also tested the fuse, and it does take 1 second to switch off, which is not fast enough to protect the power output. Power input is quite fine, but power output is probably not fast enough. So for power output, there is a 500 milliamp resistor, but this 500 milliamp resistor is, so which you see here, this fuse here, this is the 500. Let's zoom a tiny bit more. This footprint here is for the fuse, for the output fuse, which is 500 milliamps. So it is limited to 500 milliamps, but it's not fast enough. The fuse here is not fast enough. So I've added a current sensing circuit, which actually reacts a lot faster when more than 500 milliamp is drawn. Actually, more than 550 milliamp is drawn. And it indicates it switches off the power. This is in case 500 is drawn for too long, and in case the circuit fails powering off, then this will still kick in. So we've placed the fuse. This is F1. This is this one. Ferrite beads. The ferrite beads should be somewhere here. So this should be done for now because that's the inputs, and on the inputs we only have one fuse. Yeah, we only have on the, there was something did fly off, I don't know what, probably some scrap. So the beads, ferrite beads. Which are the ferrite beads? 3 amps. These are the ferrite beads. I still find them very small for 3 amps, but that's the rating. 1, 2, 3, 4. 4 of them, and since this is done, I will put it here. FB1, like ferrite bead. I have 1 for the input, so 3 amps is perfectly fine for the voltage input. We have for the 5 volts, we have 2 of them. No, we only have 1. Yeah, the 5 volts also meant just to power. So we have 7 ports on the output. Each port should be able to supply 500 milliamps, but the input is only limited to 500. So we have 1 500 milliamp input, but 7 500 milliamp outputs. So the input is not sufficient to provide 500 milliamps to all the devices if they're required. This is why we have the second 5 volt input, and I've limited to 3 amps. So this is the 5 volt. I limited to 3 amps because yeah, 6 port 5 times 500 milliamps makes 3 amps. So that's close enough, and it's rare that all the devices use 500 milliamps at the same time. This is why I've added just one 3 amp ferrite bead. And 3 amps means that the resistance is low under 3 amps, but it doesn't mean that it limits under 3 amps the input. It's not a fuse or something like that. So even if you draw more than 3 amps, it will still work. It's just not as efficient. There will be some drop, probably some drop in the voltage because the resistance is higher, but I've never tried it. And I didn't read in the datasheet what a ferrite bead, how it reacts if you draw more than the current rating. Also, it will be rare to draw more than the current rating. Dun, dun, dun. Let's hope that this design is functional. And actually, if this time the power is working on this one, I don't have to redo a board. I will continue soldering stuff on this board if the power is fine. We've added this fuse, this ferrite bead, this ferrite bead, this, and this. This is done. Next is the MOSFETs. Yeah, we have MOSFETs, diodes, voltage regulator, blah blah. Well, let's add the MOSFETs. The MOSFETs, these are 40p. I think I need to use, yep. Up, up, up. I will also use these ones afterwards. PMOS, no, that's not the right one, that's the right one. Right, 40p05, yep. These are the ones. So this is my tray with the parts. Up. I need a lot of them. Let's add some solder first. On the pads. The solder is old. It's not wetting well. And we have it on 2 inputs. So the idea is that when you plug in the external 5 volts, it disables the 5 volt input from the USB port, so we don't draw from the USB port anymore. And again, if you plug the high voltage, let's call it 12 volt, then it disconnects the 5 volt input, and the 5 volt will be generated by a buck converter. Oh, I just lost the MOSFET. It's not the cleanest MOSFET soldering, but it'll do the job. We need 2 more. And then we need the pull up, pull down resistor to switch off or on by default. I again lost the MOSFET. Luckily, these are just a couple of cents. Nah, I won't find them underground. Even if I have wood floor, I don't want to look for them on the ground. Let the insects play with whatever is lying on the ground. Come on, flip. Oh, I didn't solder the other one. Nope, I didn't. Okay, MOSFETs are soldered. We need a MOSFET for the output, but for now these are Q1, Q2, Q3, and Q4. This is done. Now we have resistors. Let me get my carousel with the common component values. Up. We want 100k. I think it's 100k. Oh, not only 10k also. But let's start with 100k. Since it's right here, 100k, 5% is fine. And 100k is, we need 2 of them, R6 and R4. I think they are right next to the, yep, they are right next to the transistors. Since they're there to bias the gate of the transistor, it makes sense to place it. You don't have to, because you can put it a bit further away, but this removes noise and this makes it easier to assemble. Because they belong to each other. So it's R4 and the second one was R6, which should be around here. Yeah, it is here. Oh, what is R3? Yeah, R3 is a 10k. Up. Okay, R6 is done. Then we need 10K. 10K, 5%, that's also fine. And this is R3. So making the design, and also what I changed is that if VBus is not enabled, the 5 volts generated by the buck converter is also not enabled. So the hub is not powered until you actually connect the USB hub. This is just because it is a USB hub, meaning that it's meant to be connected over USB. And if you don't connect it over USB, then there is something wrong. So I don't power the board. This was different the last time. It didn't care about if 5 volt was connected or not. Or 5 volt, if USB was connected or not. It just powered the. It was faulty, but it was powering the board. Actually, you had to connect it once so it started, but this was just because of a design fault. Flux looks ugly, but we'll clean the board afterwards. So that's done, that's done, this is done. Now we need the diodes. We need 2 of them, and the diodes are also there too. So D3 and D2, you still see? Yep, you can still see them. Let me switch off the DMM because you don't need it for now. DMM, this one. Okay, switched off. Which one were there? There were RB25. This is this one. They are really teeny tiny. Oh, is it this one? No, it's not this one. RB, no. I don't have on a roll. Thought I did. This is my MOSFET diode. Yeah. Okay, so they are in my diode book. MOSFET LED diodes. My diode book. And we have LED diodes. I don't think they're Schottky diodes. I think I didn't. They are Schottky diodes. Yep, they are Schottky diodes. These ones. Extremely tiny. I don't know. That's weird that I don't have them. Maybe I did order them but didn't pack them. But who cares? I have enough of them here. And I need 2 of them for now. I hate them because they're so small I can't read where the tab is. 1, 2. There is an indication, but it's very small. That's the indication. It's just there to prevent feedback. So it's making an OR of the input because the USB input is switched off when power is from 5 volts DC jack or from the 12 volts DC jack, and these Schottkys are just acting as an OR gate electrically. Could have also an OR. I think we could also have an OR logic gate, but there's no need. This is easier. Okay. Now there are plenty of other resistors which I don't know what they are for. I know what this one D1 is for. I don't care about it. But I don't know what is this. That's a USB port. I don't know what R2 is for. I think it's the it's the next one. So we did solder D3, D2, and I think R2 is somewhere in below. Where's R2? 5. R2, it's at 10k. Okay, no, I just missed it. No, I didn't solder it. R2 is at 10k. Let's go in here. Up, there we have 10k. And it's a pull-up for the 5 volt input. So these, it's rarely used, I think. Well, I don't see that very often used, but these DC barrel jacks have 3 pins. 1, 2, and 3. This is the outer shell, the outer ring. This is the inner ring, and this one, this is actually a switch. And this switch, how it works is that it is connected to ground. So yeah, this switch is connected to, well, ground, to the outer shell, as long as no plug is connected. When a plug is connected, you can actually detect it. Well, you could detect it by measuring 5 volts, but you can actually detect the presence without any voltage by just using this third tab. And this tab is disconnected from the outer ring when the plug is present. And I'm using it to actually switch on and off. This detection is used for switching on and off the voltage on the lower ones. So R2 now is done, and let's solder we could test for now, but let's solder the rest of it, which is this part here, which is the buck converter. And on the schematic, yeah, you can still see it, it's on the bottom. That's the buck converter, and now I should have the parts for the buck converter. So we have this huge capacitor, this one, C4. I already had it. It's 50 volts, 540, something like 570 microfarads. Yeah, that's it. I don't have a lot of them, but where are they? Here. I only ordered 5 of them. These ones, they are massive. And this is plus, this is minus. The plus is the long lead, the minus is where the marking is, and my footprint, the plus is marked. I have to do it first. And there is enough space, yeah. And now it's not higher than the USB port, perfect. Now I can make a case. The previous design, I didn't add the height, didn't have the height in mind, and it didn't fit. And we can cut off the leads, hold the leads while cutting off, if you don't want them to fly into your eyeballs. There's a lot of force when cutting leads. So this is done. Well, the footprint, my footprint generator didn't allow me to make it flat actually, but it's kind of an exception. I mean, just edit the footprint afterwards if you want something flat. I did edit already and had the seal screen changed. So this is this one. Then we also have a teeny tiny one. Yeah, C5, which is 1 microfarad. This is a ceramic one. This is also for fast decoupling. Yep, this one. 1 microfarad, 50 volts. I remember 10 years ago, something around that, 1 microfarad in ceramic was very expensive. You had to use tantalum, particularly for more than 1 microfarad, but now you can use ceramic with up to 10 microfarads easily. You don't have to use these pesky tantalum capacitors. This is done. I won't use it anymore. Actually, this is done also. Let's remove it from the box. C5. That's the one. Is it C5? Yes, it is C5. Tack. C5. That's done. There is R5, which is not, this is a limiting capacitor. Yep, that's the default capacitor which limits for the enabling the input. So by default, what is it? Only when VBus is present. Okay. So it's enabled low, is it? That's weird, but it seems to be the case that this XL25, if I made it this way, it probably is, but let's have a look at the datasheet. Datasheet, XL datasheet. So enable drive, enable low to turn on device. Yeah. So by default, it uses the 12 volt input itself from the 12 volts, and this puts it high. So it disables it. This is why we have a 10K resistor. Again, 10K, which is, should be somewhere around here. R5, yeah, it's this one. So by default, this buck converter is switched off until USB is plugged in, and this is why we actually have the transistor just next to it, and I need to add this transistor, which is an NMOS, which pulls to ground like NMOS do when VBus is present. So when VBus is high. This is an N-channel MOSFET, and it's this one. I also have it in rolls, but since I have my MOSFET book right here, I'll just use my MOSFET book. Always turn the boards how you would like to solder it, and since I have to solder in my left hand, I need to solder it this way. And yeah, since come on, tweezers, grab it correctly. 1, 2, 3. Up. So R5 is there, Q5 is there. Then we need this. This is one I didn't have, which I didn't order somehow. The order got lost. The buck converter, so it should be somewhere in here. This time I made double sure that it wasn't my part. There are plenty of other things, but the buck converter should be in there. Here are the MOSFETs. The MOSFET, the Schottky diodes, but there are other Schottky diodes. Oh, this is for something. This I actually need, I think. Yep, SS34. I do have SS30 more of them, and I think I will use my PowerBook first. So I won't need them. What are these? These are power distribution switches. These are the current limiting resistors, and they cut off power when the current is too high. These are USB 3 devices. These, perfect. Step down converter fixed to 5 volts. The one which we had in the previous prototype was adjustable, and salvaged it from a board. So that's done. D4, that's the one which we want afterwards. So let's put this one in. Let's put the resistors on the side, they're in the way. And yeah, I don't know, I don't think it's too important, but I have some USB traces going under these pads. I think it is okay. Probably not ideal, but I think it's okay. Else I can make it a complete all round, but it's far enough from the buck converter. Well, we'll see. If we have a USB issue while we use external power, then we know it's not okay. But it's close to the ground. There is more than 5 traces between this and the other pin, so I think it's fine. And nothing is switching really fast. I don't know what the switching frequency of this buck converter is, but I don't think, oh, this soldering iron will not be strong enough for this huge tab. I need to use something else. This one with not the cutting tip, but my soldering tip up. Let's put some water. Soldering iron pad. 480, yeah, that's okay. No, 380, no, sorry. 480 is a bit high, but 380 should be fine. Yep. And this should provide a huge, oh, maybe 380 is not good enough. Do I have to increase it? It stays at 380. No, okay. Just used a bit more time, but now it flows really nicely. And that's it. Job is done for you. I can switch it off. I don't think I have other huge. Oh, I do. No, they're not that huge. The inductor tabs. Let's try if my soldering iron, my metal soldering iron, is good enough for these tabs. So we have, this is done. We have an SS33. I think I still have some diodes here. Diode. I want to get rid of them. This is only 1 amp, so this is not good. I don't have them. Where? I think I salvaged it. That's a good question. Where did I get them from? Do I have SS33 here? These are my diodes. No, that's not big enough. That's not big enough. Yeah, I probably salvaged it from the board also. This is only 1 amp, and we want to switch 3 amps. Whoop. Okay, but a Zener, it's not a Zener diode. I have an empty. I don't know why this empty thing is in there. Huh. Weird. This one is also huge, yeah, 1 kilovolts. But we need. Where is it? SS? Didn't I put it outside? That's USB 3. We won't require it. It's for another project. This we will require, but later on. That's the power switches. SS, yeah. Here. Let's use one of them. So this is done. Cracking is probably not pleasant for you. So in theory, the marking is on the cathode, which is this one. Okay, and now the inductor. I think I didn't order the inductor. What is this? That's a microcontroller. It's not for this project. This is for this project. 20. It's for later. These are. Oh yeah, I changed it. Also, yeah, so I will remove these ones. No, it's 150, but here, 100. Previously on the output, I used the 100 microfarad for 6 volts, so it's not this one, but where are they? No, it's not this. Maybe I used everything. Maybe they were cheap enough. No, yeah, I use 100 farads, 100 farad 15 for the 5 volt output, these ones. And now I read in the documentation that for the output, it's actually recommended to have 150 farads per port and not just 100 farads. So the 100 farads, we can remove it from this project. We won't use it. We will use 150 microfarads, not farads, microfarads. Farads is too much. These are. I only ordered one from these huge pins. Okay. I don't remember. I don't use them that often, but still only one. So what is this? Shift register, another project. SMD connectors, USB connectors is another project. That's also another project. So I have to put them in the library afterwards. RGB LEDs, another project. See how many projects I have lying around. And they are huge and they're really heavy. These inductors, 33 microhenry. Yep, 33 microhenry. That's the recommended value. I didn't. Oh, there was a lonely one. I could have used this one. 9 plus 1. No. I won't use it anymore. Huge inductor. This is the recommended value from the design. I didn't do any calculation. Not sure if it's big enough. That if they add it in the recommended, it's fine. I wouldn't know how to calculate it actually. Okay, so this soldering iron is not able to solder it correctly with enough heat. Come on, the pad is not that huge. Okay, the inductor has a huge heat sink. I still believe in you. No, I don't. Let's use the other one. Plenty of heat. Yeah, really, I really like the other soldering iron. I don't know why I don't use it all the time. Probably because I got used to the Metcal because I started with it, but these Quico, yeah, Quico T12 family, they're really nice. Oh yeah, works immediately. The tips are not expensive. The performance is good. Well, it depends on the power supply you have put in behind it, but since you can choose the power supply, just use any old laptop power supply and it will do the job. Yep. It's a bit too slippery. Okay, now there's a bit more tension, and let's resolder this one. Just to have it clean. Oh yeah, that's nice soldering. These blade tips are quite nice for large pads. I use them to cut plastic and to solder really large pads, and I quite like them. And the last thing we have is the output capacitors. No, not only. So we did that. We have 2 output capacitors. which 1 microfarad. I think, yeah, it's 1 microfarad. I have some here. That's 100 nano, 16 volts, 1 microfarad. That's fine. This is 5 volt output, so 16 volt is plenty sufficient. And it's right next, it should be next to the inductor. Yeah, it is. It's right next to the inductor. And there's the last part, the 3.3 volts, which we can also solder. Bum bum bum. Up on one side. I don't know why this one was a bit hard to solder. Maybe there was a ground pad next to it. Up. And we have this 470 microfarad. I think I've seen it. Oh, this is not it. This is not it. 470. It's 6 volts, but that's okay. Plus goes here, minus goes here. We don't need to bend it, it's not too high. Let's solder 1 pin. Let's put it flat. Okay. With reheating the pin, and let's solder the other one. Up. Okay. Tweezers. Check. So we are almost done. That's the 5 volt output, and let's add the last part, which is the 3 volts. And I think, is this in power? Yeah, power voltage regulator, it's also there. I didn't sort this one out, so 1.8 volt output, I think 3.3 volt, these ones. 200 milliamp, that's plenty sufficient for our needs. It's an XH, right? Yeah. This microcontroller, this USB hub doesn't use that much power. I did have some open right there already. Hub. Here. I think we have also 1 microamp on both sides. Yeah. Microfarad. It's this one. Up. Up. Okay. This is done, and we need 2 times 1 microfarad. These are these ones. Tweezer is already getting sticky, and no, there it is. I lost the capacitor. I also remember that 1 microfarad output and input capacitor for linear regulators was really not a lot. I think on the first design I did was 2.2 or 10 microfarad, else they were not working right enough. That's changed. I think it has to do because everything has to get smaller. Okay, everything is there. Do we want to clean it or do we want to test it? We want to test it. Okay, so I will switch on the DMM. Let's de-zoom a tiny bit. Let's make that. This is done, this is done, this is done. Soldering iron, you can keep it for now. This can be, do we use it from? Yeah, we don't know. PMOS. I'll put you back in a box. You were around here. Up. This goes here. These are plenty of parts. So these, what is this? I need it. I think there are 12K resistors. This is the BIOS resistor I need for the USB hub, right? It's not written. 12K. I get it from the part number. 12K. Why didn't I write it on this? 12K. I get it from here. 1202. And this will require it. And let's put everything, all the parts not related to this project back in the box and ship it. Put it somewhere where it's not in the way. Up. We will do in the inventory later. So we have the multimeter. You see the multimeter values. Let's measure the inputs if they don't have a short. So where is my USB thingy? Here. This and USB input. So here, let's connect this and let's measure between VCC what the resistance is. 10K. Yeah, it's probably because I have 10K pull up, pull down. This is, yeah, 10K goes to ground when it is not connected. Yep. So 10K is expected. It is low though. But this is expected. Maybe I should do something else than drawing 10K all the time. Draws quite a, so 10K, this is this R3 value. 10K pulls it when 6 volt is not input, then there's a 10K. Wow, that's okay. But that looks fine. Now on the other ones, between this one and this one, we have open circuit, that's okay. This one and this one, we also have open circuit, that's okay. So for now we don't have any issues. Let's try to power it with 5 volts. This is later. You can see this one. I think you see this DMM. So let's use this one. Up, plus, and I also need the other one, minus. Let's put it to 5 volts, and I don't have any LED indicating. I just want to test if there are shorts. 5 volts. 5 volts. Should probably see. Doesn't work anymore. Maybe it's because it's not set. 5 volt, we will limit it to 100 milliamp. Should be sufficient. Set, does it? You don't see the value anymore. Does not update. Okay, there is something wrong with this thing. 303. Let's start it again. Okay, I don't know why it was wrong. now it works. So which is plus, which is minus? This is plus, this is minus. Let's switch on and let's see how much it means. Up. Yeah, 1 milliamp, that's expected because of this resistor, 10k resistor. So 1 milliamp is, that's fine. Let's measure if we have 5 volts where we expect 5 volts and if we have 3.3 volts. So ground, this, I think this is ground. This is also ground. So we have one ground pin. Let's measure the 5 volt pin. I think this one is 5 volts. Yeah, we have 5 volts on the voltage regulator input, and on the output, which here we should have 3.3 volts. This voltage regulator is not perfect, but 3.27 is fine. 3.27, yeah, that's good. Has also no load. Maybe the precision is better when it has a tiny load, but that works. Now let's test the next one, which is 5 volts on the 5 volts input. So let's disconnect this one and let's connect this one up. So now if I put 5 volts here, okay, it doesn't draw anything. That's normal because there's no load at all. The 10k is from the V-bus, it's not from on 5 volts. And is it the right one? No, it's the wrong one. Which one it is? So there was a tiny load briefly, but then nothing. So let's test it. 5 volt on the inputs, and again, this one, 3.27 on the output. That's fine. That seems to work pretty nicely. And normally, so how do I want to test it? If I plug, V-bus will always be used. But there should be no, yeah, I can't test if there's a load or not, because I don't have anything. Well, if I short actually, or if I put a resistor, let's do this. I'll put a resistor to test something. So on this there will be also 5 volts up, and this will tell us if it draws any amount. Don't I have a bigger screen? Nah, that's the biggest one. So theoretically, now I put the 5 volt from the USB. It draws some energy. This is because, yeah, this draws 17 milliamps. This one. This is why you see the 17 milliamps draw from on the power supply. And actually, it doesn't say 17. It says 7. Why does it say 7? Is it there again? Let's disconnect. If I switch off, here I see 17. Okay, the PSU is dead again. Why is this dead? I have no idea why this one was dead. Yeah, now it shows 17. That's weird. I have to test the script again over a long time. So 17 milliamps is because of this USB power meter. But it draws nothing. And now if I put a load on 5 volts, let's put a resistor. Let's put through-hole resistor. Let's put 33 ohm between 5 volts. Here we have, I think this is 5 volts, and ground, there are plenty of grounds. See, it draws 100 let's remove the limit of 100 milliamp. Let's put it to 500 milliamp. where can I put it so it doesn't bother me too much? Where are 5 volts? Well, here, it draws to, wow, this resistor gets hot. Do we see the resistor, the draw from here? Yeah, 150 milliamp. This is drawn from the USB. Normally if we now provide 5 volt from here, it should switch off the 5 volt from USB, and it should only draw 5 volt from there. So let's test it. Yep, it draws nothing, and this gets hot. Oof. So this works. If we have 5 volt input, no power is drawn from the USB. And it's also not flowing back. I have voltage prevention. Yep, so this works. Perfect. That's the right design. And the next one is if we have 12 volt inputs. That I didn't test, so let's disconnect this for now, because there will be 12 volt on there, which we don't want. Up. This will be connected to this USB thing. We know it works. Input. We will test. We will first test if there is no feedback going on. So this is on the 5 volt. Now we will set it to 12 volt voltage. Is it dead again? Maintain streaming, blah, blah, blah. Okay, that's not that important. Why is this thing dying all the time? I am at 12 volt. Where is this DMM? No such process. Inactivity from UT. Going to shut down. What the hell is going on? I have to test the script. 12 volts. So if we power, this is the 12 volt input. I'll write it also on the bottom. Well, 12 volt, 6 to 40 volts. 6 to 40 volts, and this is 5 volts, and we will remove it as soon as we clean the flux. Now if I switch on, there's absolutely no power draw, which is not, which is actually good, because there should be no 5 volt output. This should be switched off. So if I test the 5 volts, so this is ground, we don't have 5 volts, which is good. As long as we don't have USB, we shouldn't have 5 volts. Now let's connect the USB. Let's measure if there's no feedback on USB. No. So now we can connect this USB, and there should be some draw. Up. 4 milliamps, which is a good sign. And this draws nothing. It shows no draw, and if I now measure the voltage, we have 5 volt output, and it's not coming from USB, because on USB it's 5.2 volts. You probably don't see it here. It says 5.2 volts. It's behind the screen. Okay, so you don't see it. But yeah, it's 5.2 volts, and you actually don't see anything. The thing is frozen. The USB had died. So yep, so OBS is dead. So I have to restart OBS, which I'll do right now. Now it's back alive. So yeah, the USB hub detached. I don't know why. And this is also why I'm making a USB hub, which is a bit more reliant, because the one I have just keep disconnecting. But yep, so here, yeah, you probably don't see it, just believe me. That says the USB power meter says 5.2 volts, and here, here we have 5 volts, which is coming out actually from the step down converter. And if we again put the 33 microfarad, we should see that it draws nothing on USB. 33 ohm. So this is input, this is background, we see it draws more from the power supply and nothing from the USB. So it's warm. Yeah, it's probably more than what it's rated for, but it's short. It's just a play reason. So everything works as expected, which is really good. Do I clean the board or do I attach already the USB parts? Or the EEPROM? So yeah, the power works, everything works nice. Looks perfect. There's no flaw at all. Well, no flaw at all. I didn't check if the fuse works. I didn't check what happens if you draw more than 3 amps. This is not something which is there to test if the basic things was these are the extreme limits. Yeah, the next part is actually soldering the USB hub itself. I think that's what we will do. Disconnect this, let's disconnect this, switch off USB here, and let's go to the next parts and solder all the USB parts. Which is, let me show the schematic. And again, the PSU died. I don't know why. Everything in here. Yeah, my script has issues, so what? It works from time to time. That's good enough. Okay. It's getting warm here. Only 30 degrees. I thought it was more. It's a really, really sunny day. And I'm inside soldering. Okay. Now what I really hope is that the oscillator works. I had an issue with the oscillator. I had the wrong capacitors. And I think the design was bad because the impedance was not good on the capacitors. So that's the USB hub. Afterwards we don't need it. Let's put it first because it's in the middle. And where is pin 1? QFN is not that hard to solder. This is pin 1. It's getting really warm. Huge ground plane. Oh no, not you. Okay, that's not how it's done. Do I want to use hot air? I should use hot air. Maybe let's try to add some solder here. And by alternating, I just hope that at some point, it's not the only ground plane, but there are some other ground pins, but not a lot of them. No, I need to do it with hot air. So let's switch on the hot air. It's way too high. Let's switch it to 350. Come on. We'll warm it up until this flows. Let's help it a tiny bit. it sliced, that's a good sign. Let's align it. Ah, damn it. Okay. So it's not too warm, and it didn't grill. It didn't grill the chip. Let's put some flux, and let's load the SMD pins on this QFN. Hup. Plenty of flux. This will move, and we'll add some fresh solder. It has to look shiny. That looks fine, except one trace. Is it a ground trace? No, it's a USB trace. Why don't you want to look nice? And last side. Now we need to clean and inspect before we continue. So let's use one of these swabs, plenty of alcohol, and I can also clean the rest of what I've soldered. And I use these medical swabs, which are not made out of cotton and linen. This is just a kind of foam, so it doesn't lint. To clean boards, I don't really like them. Oh, this pad is not soldered well. Yeah, the one which I sold also on the other one is not. Yeah, they're not all soldered correctly. So the guess I had was, the hunch I had was right. Up. Let's clean the tip and let's try to have all the pads look shiny. Yep, this looks shiny. This pad really doesn't want to solder. Okay, now it did. This looks halfway shiny. Could be better. Okay. looks all right. Okay, last side, then we clean again and we inspect again. More flux. Clean the tip. Some solder across these pads. Don't. Okay, now it is. Why some of the pads really don't want to solder. This one doesn't want to stick. Okay, now it does. Okay, now that they all look soldered, let's clean and let's check again. And then we need to add a ton of capacitors. This looks okay. Doesn't look okay. Flux again. Now it looks okay. Let's hope. I think it's not. No, just clean that. This side looks fine. This like actually awesome. Nah, not awesome. There's one which didn't solder. Yep, there's a one which didn't solder. Okay, now it did. What's this pin? Is it actually connected to anything? Okay. That's soldered. Up. So now we need to put a lot of decoupling capacitors. Do we want to solder the EEPROM first? Let's add the capacitors. So let's add all the one microfarad capacitors. We have C11. power input was working. And I lost my, no, here it is. C11, where are you? 12, 13, 15, 11, here. Oh, this tip is used. Let's refresh the tip. Trust with some flux. Okay. Why don't you want to solder? Okay. C11, that's done. C9. C9 is this one. It's a bit far away from the pad, but I wasn't able to sneak to have enough trace for all USB ports to sneak correctly. I think it's a lot easier with, and I think this is meant for 0402 resistors and not 0603, but they're a bit harder to solder by hand. They start to get uncomfortable. It's still doable by hand, but it's not pleasant. So C9 is done. C15. C15 is this one. Yep, it's this one. Probably I'm overdoing with the decoupling capacitors, but I really only reuse the ones per rail. I have one 100 and then 100 microfarad per pin, per IO. And it's just because they're really cheap and they make things a lot more stable. So C15 is done. Check C13. It's somewhere around here. C13 is this one. Up. That's C13. That's done. C20 and C22. C20 should be around here. Yep. So at least I have one per side, which is a good thing. C20. And C22 is the last one. Up. Where are you? Somewhere here? Yeah. C22. C20, C22, all the other ones are 100 nanofarad capacitors. some solder. This is also 100. Yep. This is 100. This is 100. This is a resistor. This is 100. This is 100. This is 100. This is a resistor. That's 100. That's 100. Resistor, capacitor. I think there is also one around here. Yep. That's it? No. What is this one doing? Ah, this is actually C25. Yeah, it's for V-bus stabilization. C23. I really hope first I didn't kill IC because it's too warm, but I don't think so. What I'm really afraid of is the clock. Although now I have the right capacitors, I didn't put any ground under the tray, so the coupling should be nice. So the impedance should not be too much affected. I think it's okay. It was just a traumatic experience with the previous design, where I needed to build an external clock reference to inject 24 megahertz. Yeah. Up. Next capacitor. This is also capacitor C14. Oh yeah, it is. It's weird the way I put it, but I think I didn't have any place to do it another way. Oh, it's super far away from the pin. I hope it works okay. Up. On the other side now. Yeah, and I have to put the EEPROM else it won't boot. That's the boring part on these capacitors. I don't think I need to change a lot in the EEPROM. I think what I need to change is that the downstream facing ports are not swapped. But for now, since we didn't solder any downstream facing ports, it's not important. Do we have some capacitors? Oh, C24, what is this? C24. That's for reset. I have 23. Why is it so far above C24? Ah, yeah, it's for the reset pin. That's not too critical. So reset doesn't change too much. So that's why it's so far away. There's nothing in between which should influence it too much. Up C12. This one. C25, which is for the EEPROM. Okay, the EEPROM only needs 100 microfarad. I think it's not a lot, but it did work the last time. Okay, it's all of them. This is for the downstream tracing ports. Yep, it's all of them. So let's add the resistor. R12, I think, is 12. Yeah, R12 is the one with 12. Where did I add it? 12K. This is, I don't know why, but apparently it's the reference voltage and it's 1%. Or for the PLL, I don't know what it's used for. But I'm surprised that it's not integrated in the AC and you have to provide it externally. Not too much of an analog designer. Where did I put it? Where are you? I don't know. Ah, here. It was next to R12. It was sticking on the board. Up. So we added all these capacitors. Tack, tack, tack. It's done. 25 is also done. 24 is done. R12 is done. 23 is done. Now we have R10 is 100 is 10K. And then we have also 100K. 100K is R15. It should be somewhere here. Yep. R15, then 100K is also R11, right? Yes, R11. Which is for VBus. Yeah, to detect VBus, it pulls it low. R11 is the bottom one. Let's turn this around. 10K, 10K here. Don't I have 10K 5% somewhere to get rid of? No. 10K 1%, still have thousands of them. Okay. What is R22? 2022. Okay, that's this. So what is R13? I did R15, right? Yes, I did 15. 13, it's 100K, and 14 is also 100K. These are config resistors, and I could tie them to ground or VCC and not really use a resistor, but resistors allow me to change it on the board if I want to do something else. That's 14 and 22 now. 11 is done also. 13. 13 is 14K. 100K. Yeah, so if I want to change the value, I just desolder the chip and connect it to ground using a wire. The chip meaning the resistor. Up. Okay. Where is R14? Here. That's the one. You're also 100K. This one is far away. Also, so the first layer is all the signals, most of the signals, and all of the how they call it, all of the differential pairs of USB, because changing layer changes the impedance a lot. So I want them to go directly to the connector and only then change the layer on the bottom. And you don't want stubs. So you would like it to come on from the bottom of the USB connector and not from the top of the USB connector, but else as it would create a mini stub antenna. This is why they are all on the same side. So on the front top side, the most important is just all the differential signal. I have a couple of non-differential signal LEDs and things like that. So other kind of signals on the bottom. The second layer is only ground, and the third layer is the power domains. We have V target on the outside, and we have 5 volt, and then we have 3 volt, which is almost only around here. So what is R20? So R10, R11 is done. R10, R11 is done. R13, R14 is done. What is R22? Where's R22? Did I cross it although I didn't put it? No, R22. It's this one. It's these three. Okay. These are the I2C resistors 4K. Do I have them here? 4.7K. Yes, I do. So 4.7K, the only place I use them is as pull-up resistors for I2C. Between 1K and 10K. 10K for 100 kilohertz is okay. 1K when I want to use 400 kilohertz, I think. And 4.7 are both for both actually. or at least one, maybe 1K is for 1 megahertz, I don't remember. But 4.7 are fine for 400 kilohertz. I don't think it uses 400 kilohertz. It only needs to read the config or during boot once, and it's only 100, 256, 128 bits. I don't remember. It's really not a lot. That's read fast. Up. This resistor. Then I need to find the I2C from. Then I can solder the connector. Dupont cases, header pins. Here, header pins. I'll use yellow because I still have some. Check. This. Up. Go here. Let's do it this way around. Let's get a tiny bit of solder just so it sticks. That's probably ground, so it won't stick to ground. So let's try on this pin. Okay, so this holds. Okay. Okay. Headers is done. Let's get the I2C EEPROM. So that's done. That's done. I think this is in my IC. Yep, it should be lying here. ICs, and I should have EEPROM here. Should be one of them. This one. In this tiny SOT23 package, instead of the usual SOT8 SOP8. They are nice, small. That means just EEPROM. If I have a lot of space, I use the old SOP package because I have enough chips. But for tiny designs, I use the tiny package, which is fine. Oh, I shouldn't have put the header. Now I have issues soldering. Let's turn it. Yeah, I remember my rules. Put the tall first things in the middle, then go outside, then pull the tall parts. I didn't respect my own rules. And now I have issues soldering it. But my skills allow me to do it. It works, so the EEPROM is there. We need to program the EEPROM. We'll do it afterwards. Does it boot without the EEPROM? I don't remember. Let's put the crystal. So now we have the 20 picofarad, the right one, which is matched for the crystal. So use the value on the crystal. I think in theory you should also maybe calculate your impedance based on the traces and so on. But I just take the one from the crystal. I'm not good at analog design. I've never learned it like any electronics. I just learn by doing. and most of the time it works good enough. Well, last time it didn't. I used 18 picofarad instead of 20, and I probably had some copper right beneath the traces, and it made that it didn't boot all the time. Here I'm also a tiny bit afraid the traces are a bit long. They go from there to there, but I didn't have the space to put anything. The decoupling capacitors are more important than the crystal, but who knows? Maybe I am wrong. Where are my crystals? 24 megahertz. And I need to use hot air for that. Up. So let's put some solder on the pads, and then let's connect it using hot air. I think it's not important which one is which side, since it's symmetrical. But let's try to do it the correct way. This is pin 1, this is pin 1. Okay, hot air. Dun dun dun. Let's heat the board all around. Starting to melt. Yep. Let's clean the excess solder. Hup. Now we can try the EEPROM, and then we can try to boot if it works. Just let's measure the resistance between 3 volts and ground to see if I didn't create any shorts. Resistance, I think this, yeah, my script failed again. What is ground and 3 volt? This 10k. That's okay. I think I have a put up or pull down. That's fine. Up. Clean the board. Yeah, let's clean the board. I think I'll need rework, and I'm sure there will be some fixes and some mistakes. Let's clean the board still. Ugh, this looks ugly. Okay. My EEPROM programmer. I thought I had a kind of wire thingy for it. Now I need to, well, let me clean a tiny bit the place so I can switch the camera. For now I will put you to rest. Switch off, put some solder on the tip while it's resting. Does this camera work? This is the audio. This doesn't have to be the way. That's another project. That's another project. Let's put this here. Okay, let's try if we can. I have no idea why this doesn't work. Let's try if I can switch the camera. Yeah, works. That's nice. Let me get my hands clean and remove all this lead. Up. Okay, now I'm allowed to lick fingers again. Let's get the board. Yeah. That's the board. We need a lot of pins. To connect this, and I need to remember the footprint of I2C EEPROM. Did I change the cable? Yes, I did. Footprint for I2C EEPROM. Sub 8. Why are you such a pain? Do I really have to get the data sheet? Data sheets. I see EEPROM. Okay. We don't need this anymore. So that's the footprint for standard I2C EEPROM. Let's get some cables. We need female, male. How many pins do we need? 6, and then this. 2, 4, 6. Yep. That's 4. 2, 4, 6. That should be fine. Up. That's open. That's the pin 1. So we will put VCC. That's this one. Crown is probably 1, 2, 3, 4. It's this one. Connects these two first. Then we have white protects. Okay, let's connect them. Ground 3.3 volts. I hope it's outputting 3.3 volts and not 5 volts, but I don't think so. Then this kind of orange, this is right protects. The reset needs to be tied low. I think it's low. Low is reset. Let's use yellow. So yellow will also be connected to ground. Up. Yellow is connected to ground. Up. Then we have green will become the clock and blue will become data. Clock data. Okay. The same, so I don't need to change the. I don't need to change the EEPROM. Doesn't. Wrong cable. Which one is my? This is too. No, it's not too short. Up. EEPROM. Okay, EEPROM is connected. Let's test. Let me switch to a screen. Not this one. Full screen. This one. Project USB hub. I think it's in here. EEPROM.bin. Yeah. Let's EEPROM. This one. Let's try it this way. Overcurrent protection. Damn it. Yeah, it draws a tiny bit more current, but it shouldn't draw too much current. Let's just try to provide a USB 5 volts. This should be good enough. It shouldn't draw too much. Okay. So we have no USB input at all. Verification failed. I love when verification fails. Again, at the same address. You are under reset. You should do nothing. 1, 2, 3, 4. Let's remove VCC. It's still at this verification at address. Okay, file. So it fails to write anything. Did I connect the write protect correctly? Write protect. It should complain from the beginning. Yeah, but we know that this is not a good one. So reset is yellow. It is hold to ground. That's okay. Write protect. Something not solid correctly. I don't think so. Let's try again. Green is clock and then we have data. Green is clock and then we have data. No, the pin is correct. This is this. Okay, this was not connected right. The clock one. Come on. All these pins are correct. All these pins are correct. Why are you failing at writing? Do I really have to take my oscilloscope out? Is something getting warm? How much current is it using? So let's get the USB power meter. 100 milliamp? That's quite a lot. It shouldn't draw 100 milliamp. It does nothing. Okay, there's something wrong. There's a short somewhere, or something like that. This should never draw 100 milliamp. Yep, 140 milliamp. There is something wrong. Do I have to get my infrared camera to find out which one it is? 140 milliamp. That's not good. Let's measure the resistance. Is it between the 5 volt or the 3 volts? Resistance between 5 volts okay, I can't measure because it automatically drains something. So let's try between 3 volts 15k. That looks fine. So there's something while powered on. Is this a short? Is there a short somewhere here? Did I connect something wrong on the USB chip? I hope not. Who is drawing too much current? Let me get my infrared camera. Too lazy to troubleshoot it. So where is it? Let's hope the phone still has battery, else I can't use the camera. Nope, it doesn't. The battery is dead. Damn it. Let's try here. If we provide 100, let's go to the bench. And there is something wrong. Shouldn't draw 100 milliamp. Far too much. So up we will use. Let's switch camera up. Let me put you to the bench. Bench. I need this one. This is 3 to 3 volts. I need this one up. This is ground. Let's set it to 3 volts. Okay, on. Draws 50 milliamps, not 100. What? Why should the 5 volt 70 milliamps? It's still a lot, but it's nothing that fancy. Why on the 5 volts would it draw 100 milliamp? Maybe the power meter, no, draws twice as much on the 5 volts. That's a lot. Let's try to find out. Now it draws nothing. Let's connect it here. Up. What is P minus? This is minus. This one is plus. Plus clip. Yeah, I think I will use my second. No, it doesn't use. Now it uses 60 milliamp. Yeah, in the 5 volt input. That's okay. It's not too much. And probably also now this shouldn't power back. I don't know why it complains. That's not too much. It's still a lot for doing nothing, but it's nothing extraordinary. To have a look at the EEPROM trace. I'm too lazy to. Can I use some other debugger? Yes, I could. My own, actually. What do I want to do? I would like to see who heats up. That would be nice. I can test with my... Do I have enough pins to do that? I think I remember there was a fail. Right, protects. So this is a super old project. I don't know if it still works. Busvoodoo dongle. Yeah, you have no power at all. 0%. Yeah, you have to charge. Always when you want to use it, it doesn't work. So let me try my other project. What is this? 3 volt ground. I will have to cheat though. I don't have enough pins. I'm missing 2 pins. Write protect must, it is high, so it must be connected to ground too. To write it, everything must be connected to ground. So let me try my way. Do I have a multiple ground thingy? So I'll show you some project I've never published, although it is available if you look for it correctly. Switch up. The Busvoodoo, a multi-purpose debugger which is capable of plenty of the low TTL protocols like you are used to, SPI, UART, I2C, blah blah blah, and also some non-CMOS protocols or non-TTL protocols like CAN, RS-485, RS-232 here. The idea was to have some kind of a bus pirate. Same idea as a bus pirate, but everything is embedded, so you don't need any external software. It is capable of higher voltage and it shows the pinout. Where is... this is a bit too short. Tack. Yeah. The screen is broken. How can I show you? I need USB so you can see what I'm doing. Up, tack. So that's the device. When you plug in, it's in high Z mode. You see the mode. I don't see it. No, you can see it. It says high Z. And then it shows the pinout, and that's the default pinout. You could even set some voltage. It was 5 volt tolerance, 3.3 volt voltage, 3.3 volts capable. And what I can do is minus D dev TTY ACM0. It's not minus. Minus B for device. Don't remember. Is B not the baud rate? No. Come on. It's just device. It's just P-com. It's not minus D. D is probably data. See, welcome to the Busvoodoo. You don't see anything, sorry. Full screen. This screen here. When you connected, welcome to Busvoodoo, and you had 2 options. One which was a bit more expensive, the full version where you had the non-CMOS protocols, and the light version with the CMOS protocol. But it turns out it's not a good idea. There are several flaws on this product. It's not a good idea to have two versions, only have one version of a product. It makes it a lot easier. I wanted to have the non-CMOS. So it's the same board for both of them. I wanted to have the non-CMOS a bit cheaper. And the CMOS version a bit cheaper and all non-CMOS protocol a bit more expensive. This is where we'd make the money and make almost no money on the simpler one. Having two versions makes just things complicated. The other fault is, well, which now is a fault, is I used a standard case with a micro mini USB. USB-C was not common when I designed it, and micro USB was just too crappy. The connectors just go everywhere. I really preferred mini USB, and I had a really small case. I wanted to be a small tool, so I had a small case with it. No one has mini USB anymore. I would switch to USB-C, and this screen breaks a lot because it's on the outside. I need to design my own case with the screen inside. So my product never made it out, although if I have time, I'll still make it. What I did though, in exchange, is have this one, the third version, the Buzzword dongle, and it's you just reuse the part of an ST-Link V2. So all the components would be on one of these ST-Link V2 clones. You just need another board, which I provide. You solder all the desolder on the components from the ST-Link V2. You solder all the components on the new board, and then you had the same functions, but a bit more. So no non-CMOS protocols, but it's really small, and it works the same way. So now we are connected. If we press mode, we can say the mode. We want I2C. Now I2C, we want 100 kilohertz, 7 bits. Open drain, we have embedded pull-up resistors. Yes. Use to set pull-up voltage. I think it's LV 3.3, like that. Yeah. So we also had, I don't remember how I did it. I don't remember. I think I have a DAC which powers an adjustable voltage regulator. Yeah, that's it. I have a DAC with an adjustable voltage regulator, and this way you can provide voltages from set voltages from 0 to 5 volts. Don't remember. So now the voltage is set up. I just need to connect all the pins. We will use this what it's meant to, and this allows low-level protocol debugging, and here we can see what the issues are and so on. This is why I will use this one, because yep, the programmer should have recognized from the beginning that it failed writing. So I need cables, female. 1, 2, 3, 4, that should be enough. No, it's more, but I need also to multiply the grounds. I only have one ground and I need more than one ground. How will I do it? I need ground on reset and voltage protect. I could cheat on the board, or I could have, I do have normally, I think I do have them here. Yep, I have some. Up. Yeah, I have some ground bars. Connect one ground to plenty of them. And I just need to. So, and here, yeah, you see the pinout is shown on the device. So we know where to connect things. So we have ground. So it's a nice product. It's just kind of flaws, and I've never managed to complete it. And now I think it's not doable anymore because STM32, it uses an STM32. STM32 is just not available anymore. Up. up. So we have VCC, and then the orange is STA, yellow is clock. And if it doesn't work, then I will just use the logic analyzer. And the ground, we'll get it on the ground bar. And we need 3 ground pins. Up, wrong cable. That's not 3, that's 4. 4 is also okay. One, two, three, 4. 1, 2, 3. And we need write protect on ground, so we can write. We need ground on ground, and we need the reset on ground, so it holds the MCU in the reset. Up, up, and that's it. Now they're connected, and now how does it work again? So you see all the commands, you didn't need any external utility. All the commands were in the microcontroller. And reset I2C, reset I2C, yeah, I remember why. Actions A, we can do all these actions. So start, then we select slave to read. What's the default address of these devices? I don't remember. 050, something like that. Where's the default address? Address. What's the default address? I think it's, I can actually, there was, is it not here? Did I have a scan tool? Yes, scan for slave devices. Error detected on bus. Ooh. This one was the pain points. The I2C peripheral on the STM32 is such a pain. But this indicates we have an error on the I2C. I shouldn't use an internal resistor. Let's try again. I have external ones. Yeah, the I2C on the STM32 is just so hard to drive with external resistors and scan. We need to, no, we do provide power. We do provide 3.3 volts. Maybe I need to switch on the 3.3 volts. Help. Power. That's it. Switch on. I need to power the device. Off. Power. No, that's pin out. Power off. Power on. Now it provides power. And it measures. Oh, I didn't remember that. It measures correctly. It measures the power again. Now I should be able to scan. 0 I2C devices slave. 0 slave found. Well, the I2C EEPROM is dead. Or there is a problem on the connections. But that explains why I can't program it. And this is why, yeah. Who developed this program, this EEPROM programmer? This one, who is not able to even scan if a device is here or not and check before it writes. This is really bad written firmware. So, at least now we know that there is no I2C EEPROM. Why is there no I2C EEPROM? I don't know. We know where the failure is though. I could test the logic analyzer to see, or the oscilloscope to check which of the signals is low, which of the signals is high, if it does the scanning correctly. always makes things complicated. Let me check my schematic if I did everything okay. Let's get the data sheet. No, I didn't change that, so that should be fine. STL, STA, VP. Let's test if I didn't mix both of them in the board design. Board. Where is the design? TX, yeah. Here's the bottom view. We want the top view, but we want it this way. So SCL is correct. STA is correct. This is this one. STA goes here. There's the pull-up resistor right here with the 3 volts. And that's only the 2 signals. So let's check with the logic analyzer up where the problem could be. If it does actually scan correctly on the I2C bus, if everything is pulled up correctly. Up. Dun, dun, dun. Up. So we need one ground. Actually the ground, we have a ground bar, so I can connect it to the ground bar. And then we have 2 signals, 1 and 2. One. Two. We want SCL and SDA. Which one is which one? I don't know. So let's put the first one on clock. No, that's data. And this one on clock. Did I do it correctly? Oh no, I didn't. No, I did. Okay. I did connect correctly. Okay. Up. Logic analyzer is connected. Let's try to figure out. Let's start the logic analyzer. I don't need you for now. I don't need you anymore. Pulse view. Pulse view. You are in my way. Let's try a new session. Oh, I can't. What was this? So this is SDA. No, this clock. SCL. SCL. That's SDA. I choose 1 megahertz. 1 sample. That's okay. The clock goes low. We want to trigger at 5%, pre-trigger at 5%, and we don't want these ones. We only want the 2 first ones. Okay, so if I scan, well, if you're not sending something on a data, we see the clock is correct, but it transmits nothing on data. I'm not sure if it's because I'm not transmitting anything. Let's try to find out. So clock, this is data. And let's try, but this is not pulled up anymore. Let's have the pull up resistor embedded. I2C, we 100 kilohertz, 7 bits. We want the internal pull-up resistor, 3.3 L, 3.3 volts. That's okay. What is with power? Power is off. Don't care. We need for the clock. Power on. Power is on. Now let's try to scan again. I hate the I2C on this STM. I added so many time on and spent so much time, but yeah, I would do this thing differently. I wouldn't use STM anymore because the STM are not available. Let's try again. Scan. Why aren't they pulled up? It looks... Oh, that looks okay. And it's the I2C is blocked again. I2C is so hard. The STM32. Let's do it the other way around. We have still... Let's not try to use my device, which we've seen can't do I2C. Let's try to sniff the programmer. I don't have enough USB ports. So programmer. One. Two. And ground. Okay. And I don't have enough USB cables. Oh. Let's do it the other way around. Let's do it this way. This goes here. Yep. Micro USB inputs. Up. Let's get another USB cable. Yeah, this one. So the target is powered. It shouldn't drain too much power from the programmer. So let's try the programmer and see what it does. Nothing. Because we are missing the signals. Now it's trying to do something. So what are you complaining about? Write code. You're not writing anything. Why is it using 150 milliamp at 5 volts? I think my power meter is completely wrong. And why aren't you detecting the data? Is the pinout wrong? What is the pinout for this? 80, wasn't this the pinout I was looking for? Yes, it is. VCC, that's okay. Ground, 1, 2, 3, 4, that's okay. Right protect, that's okay. Right protect the third, 1, 2, 3, yes. Then we have clock, that's fine. Blue, data. Why aren't you showing any traffic? Oh, there is a tiny bit of traffic. Yeah, there's something wrong with the with the data. The data is always pulled up. Seems to be shorted to VCC. I don't know why. So there's something wrong with data. Let's test the resistors. You don't need. Maybe I need you. I don't remember. I don't need you though. Up. Let's go back to the bench. Have the 3.3 volts. Switch off. Ground. 3 volts. Let's measure first. Multimeter leads. You are here. We are in ohm. That's good. And let's try to measure. What? 3.7K? It's a bit low. It should be 4.5, 4.7K. If I do it the other way around, 3.9. That's weird. 4.7. That looks fine. And the other one is this one, I think, C22, 4.4. That's also not a lot. What is wrong with these resistors? So this is between VCC and here the 0, that's normal. 4.8, okay. 0, it's normal. 3.6, this resistor has an issue. 4.7. So let's heat it up and let's put another 4.7. Come on, so you don't see anything. Were you not seeing what I'm doing? Here it is. Come on, heat up. Somehow I have the feeling it was faster in the past. It's probably just me getting impatient. And was this actually the data pin? R20. No, it was the clock, but the clock was working. The soldering iron so I can desolder correctly. Up. Okay, now it works. Maybe it was because... No, but this chip was held under reset. It should do nothing. And it seems correct. Let's try to measure again. Between this pin and... So this pin's at 0. 15 kilo. Okay. Is this okay? Followed 8, that's okay. Followed 7, that's okay. It's charging. Here is a capacitor charging. We see the voltage is going up. And you don't see anymore because this stupid script died again. There is inactivity. Why didn't... Normally there wasn't inactivity, it should restart. There's something wrong with my script. Do I want to try to flash the EEPROM outside and then I can solder it on? Do I have an adapter board? I don't think so. I don't think I have an adapter board to flash it. But at least it would show if the EEPROM is dead or if it's the fault of the USB hub. I could desolder it, solder pins directly on it, or at least have a board. I do have some adapter boards. Something for this kind of sub 23. Sure, I have some. Maybe. Would this work? I don't know. Let's unsolder it using hot air and let's program it. On separately. If it works separately, we know the issue is not the EEPROM, but most likely the USB hub. Come on, get off. It's melting the plastic next to the plastic header. Okay. Okay, so can it fit on there? Yeah, it can. Oh, there's one of this there, I don't care. Yep. Ugh. These boards are so old. Solder doesn't stick to it. Up. One, two. You're not seeing what I'm doing. I'm just soldering this EEPROM on an adapter board. 3. We have 4-pin headers somewhere around here. They're not all 4 pins. Sure, I do have some 4 pins. Not 4 pins. Now we have 4 pins. Up, prototype board. This. Up. Let's solder the EEPROM. Maybe I even, no, I'm not sure. I have an adapter for it. I could though. There's so many of them. Done is done. Yeah, I should have used an adapter. I think I do have an adapter for this thing, but yeah, now it's done. So, just need to put it on here somehow. Just have to connect it. I only need 4 cables. I can remove this. Do I have to switch? Let's switch the camera. Yep. So, on this datasheet, what is what? Data sheets. This is this one. We have here this one. So 23. So that's pin 1. That's pin 1. That's okay. That's pin 1. 1 is SCL. 2 is ground. 3 is SDA. 4 is VCC. And 5 is write protect. Up. On this one, we have VCC here. No, that's okay. VCC, then write protect. Write protect is the 5th one. It's gray. Write protect. Then SCL. SCL is the first pin 1. It's orange. And then white. And on the opposite side we have ground. Up. Now it is connected, and now let's try if it can flash it. Up. Verification okay, so it's not the EEPROM. Yep, verification okay. Yep, as expected, the EEPROM wasn't the culprit one. So I think the USB hub has an issue. Let's unsolder the EEPROM, put it back. Where's this here? Put it back on the board. And try to figure out where the culprit is. I do have that thing. This I don't need anymore. Here. Yeah, heating up, unsoldering, desoldering is probably not good for the components. They'll survive. Okay, that's unsoldered. Let's solder it back to the board. I need to clean the board first. Let's get some solder breads up. 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 Oh, not these scissors. I have a cutter. Tack. Let's put some flux on the pad and on the wick, because this wick has no flux inside, so we need to add it. And now let's try to wick to solder. Come on, wick, get warm. So you can wick to solder. A bit more. Okay, now it's getting warm. Okay, good enough. Up. Here's the EEPROM. Up. Okay, the EEPROM is soldered. Let's put another of these folded 7K, but I'm sure it doesn't matter because that's not the issue. Probably the camera is warm enough. The battery is good enough, and I can try the infrared camera. It had a bit of time to recharge. The battery. Sometimes on this iron, this is getting really warm when it's stuck in here. I don't know if this should be the case. Okay. Yeah, maybe there's a connection issue on here. Let's try again. See if it still draws that much. 3.3 volts. VBus detect. Let's try directly to connect to the computer and see if it's detected. No, nothing. No USB, nothing. I think the USB is disconnected, right? Yeah. No USB activity at all. I know why USB, no USB activity, because I didn't put any USB, the TVS. Yeah. Forgot to put one of the components on it. MOSFET diode, I think it's, not sure if it's in here. I know I have some in here. power MOSFET LED diodes, TVS, yes, and I want the 2 bits, I think it's these ones, yeah. I have to add this one, else I can't have any USB. Up, up, up. The USB port is here. This little device, I didn't add it. Without this one, well, you can't have USB. Oh, where's pin 1? Oh, damn it, I don't see anything. I think this is pin 1. No, the other way around. Ah, damn it. Yeah, this seems to be pin 1. Yeah, so it was the right way. USB looks ugly. The USB, the chip looks ugly. And let's add some lubricants. And it works immediately better. Let's clean and let's see if it's really pin 1 using some light and some magnifying glass. Lights, there should be a switch somewhere here for the lights. I don't need you. Don't need you. Yeah, pin 1 is correct. And is this dead again? Yep. Right, is it dead? Yeah, OBS is dead. Let me. And we should be back. Come on, OBS is streaming. Should all be fine. Yeah. Now we're back. So let's connect USB and let's see if it does something. No. Okay. Nothing. When we connect, we have no activity at all. So is it again a problem with the clock? Come on. We can see if it's starting, if it starts reading the EEPROM when we connect to its, that's ground. Then we know if it's a clock issue again or if it's an EEPROM issue, a chip issue in general. That's we don't need anymore. That's going Up. So PA, no, that's not the right one. Oh, pulse view, I'm getting tired. Something is getting warm. That's okay, 5%. And we want 1 megahertz, and we want when the clock goes low. Up. So let's start. Let's try. No, 1 megasample should be fine. Doesn't read anything. So yep, the USB device is fried. You don't see what I'm doing. Full screen this way. So let's start again. App restart, and when we plug in, we should see some I2C traffic for it reading the EEPROM. You see, nothing. So we know the USB hub has an issue. Let's desolder it and resolder it and see if this does anything. And we saw last time that even with before I do that, the thing is probably correct. Let's cool it off. We saw last time that it can read EEPROM even if the clock is not there. Last time in one of the previous stream, we saw that it can read the EEPROM. The clock, the 40 megahertz crystal, even if this one is not started, it using the internal oscillator probably, it can read the data. So is the phone charged enough? Yes. Let's try to see with the infrared camera if something is getting warm. Okay, here's the infrared camera. Let's try to focus on something. Okay, here we can kind of see the chip, the USB hub. Let's try to plug it in. Oh, yep. You see, the LDO is getting warm because it's supplying a lot of current. This chip is getting warm inside here. So either it is fried or it is wrongly soldered. Let's try to resolder it. And if resoldering isn't enough, then we'll solder a new one. But I probably put too much on the ground pads. And the LDO can only drive 200 milliamps, so that's a kind of a limit. So, switch the camera. You need to go to the bench. I didn't switch the camera. Switch the camera. Okay. I don't see any shorts on the side, so I think it's on the bottom that something happened, or between the bottom and the sides. So let's remove it. Let's clean all the pads. Let's resolder it, and let's try it again. Not these tweezers because they remove heat. Let's use these tweezers. Damn it, I'm so stupid. This is pin 1 marking, and my board pin 1 marking is right there. No wonder it doesn't work. Now the question is, did it survive it? If it's the wrong way around, or does it break something? That's a good question. Well, let's try it out. We will desolder, clean the pads, resolder the right way around. If it doesn't work with this chip, then this chip goes to garbage. We will use another chip. I have 3 of them remaining. They're still expensive, I think $7, something like that. So they're not too cheap. I think that was the issue. Okay, let's clean the pads. Solder wick, we still have some. Let's put plenty of flux so we can clean the pads. No wonder nothing was working. And no one in the stream is there to tell me such stupid mistakes. Well, I think we don't have to clean the chip itself. This is pin 1. If it survived, it's quite a robust chip, so it's well made. And well, it's one of the more expensive ones, so I wouldn't be too surprised. It would be nice. Let's heat up. Oh, let's put some flux again so we can solder the bottom and all the sides. Good enough. Pin 1 is here. Whoop. Yeah, there's enough ground on the bottom. The footprint generator can't make center tabs the perfect way. Normally you don't have solder paste everywhere. You have some openings. Okay, the board should be warm enough. Ah, ouch. Okay. That seems okay. More flux on the sides. Let's solder. If it works, then it's a miracle. Because some VCC and ground pins have not been correct. Else we'll just use something else. Soldering is smooth now, at least. That's a start. Did I burn myself with the tweezers? Maybe just slightly. Still not comfortable. This one is done. We put a tiny bit of water. I didn't expect the ceramic tweezers to transfer heat that fast. Let's continue soldering. Always the same pad. We don't want to solder. Which, they're not people, so which. Okay, that looks fine. Too much solder. Oh, but it looks fine though. Except this one, which we know. Okay, and last side. These pins don't have enough flux and enough solder. Yep. That doesn't look okay. No, it looks okay. Well, let's see once we clean it up. Hup, plenty of alcohol. Now, hup. It's not perfect, but I think the contacts are there. Yeah, I think it's contacting. Let's just try to see if there's a short. If not, I'll connect it directly to USB and then we call it a day, because I can concentrate. Perfectly more ground. 3 volts, switch on. It uses only 32 milliamp, so that's already a change. It's not 60. Let's try to connect over USB. Full screen. Without checking if it reads the USB, the EEPROM. No. Oh. It kind of works. There is something wrong on enumerate device. Which one? On port 1. Yeah, that's not an issue. So it works. That was the issue and it survived it. Let's try to plug again. So it's normal that you're not able to enumerate anything on downstream because there is no downstream. It was me with the fingers. Power cycle, unable to enumerate USB. Okay, you still have a bit of quite some issues. Is it because of the trace? No, it's not possible because the switch is not here. Is it again because of the clock? Come on, if it's again because of the clock, killing myself. It seems to be because of that. If I put my finger on, don't see it. If I put my finger on it, it works. This clock is really sensitive. See, if I don't connect, can't read. I put my finger on the clock, change the impedance a tiny bit. It seems to work sometime. Yeah, and then it doesn't work again. Ah, it's not perfect. I have to look at the oscillator if the clock is running correctly, if it's managing to start it correctly. But it's a progress. Maybe this chip is just too damaged now. We desoldered it it was soldered the wrong way. We desoldered it. Maybe it's because this chip is defective. Although it did manage to work once, it does something. Yeah, probably the chip is defect. Yeah, I'll check at the clock if it's running correctly. I don't know how. With an oscilloscope, probably. If we have 24 megahertz. And else, I don't know, maybe the chip is really defective. We destroyed it partially because we soldered it wrong. But else it seems to work. That's it. That's done. I'm closing the stream. Enjoy the rest of the evening, and I'll probably show you more results, and there will be another stream to do the downstream port once I figure out why this doesn't enumerate correctly. First it has to enumerate, but until then, enjoy.